Good day, viewers. The topic I'm going to teach, the subject I'm going to teach is mathematics, and we are going to look at cycle theorems. Now, before we go into cycle theorems, there is a need for us to know some parts of a cycle. That is before we proceed. Now, here we have a cycle. Now, from this cycle here, now AB here is a chord. So a chord, it mustn't be equal. You may have major chord and minor chord. So AB is a chord. Now you have this portion that is shaded here is what we call minor segment. Then if you look at here, O is the center of the cycle. Then COD is the diameter. Then we have OE, OC, OD is the radius. So that is OC is the radius of the cycle, OE is the radius of the cycle, or OD. But COD is the diameter. Now, this is the circumference here. You can see the arrow here. So this is the circumference here. Now, this part here is a minor sector. This shaded part here, that is COE, this part is minor sector. Now, let's look at some basic concepts that we have. Now, first, we'll start with the radius. What do you mean by radius? The distance from the center of the cycle to any part of the circumference is called the radius. Now, look at the diagram here. So, the radius, now, this is this distance here, this is the center to the circumference here. So that is what we call the radius. Now, the next we have is diameter. Now let's look at diameter. Diameter, this is the line. This is the line that is cut, dividing the cycle into two equal parts. That is the line passing through the center from one end of the center of the circumference to the other end. Now this is a diameter. Let's come back here. Let's come back here from the definition. So the diameter is the distance from this to this. From this end to this is the diameter. Now let's look at chord. Now for the chord, it is a line from one end of the cycle of the circumference to the other end, dividing the cycle into two equal parts or segment. So let's look at the diagram again. Let's look at the diagram. Now if you look at the diagram, AB is a chord. Now I may decide to erase this. I have CD, it's also a chord. Now that is what the chord is. Now let's look at segment. Now segment, it is the area divided by a chord. The small area is a minor segment, and the larger area is a major segment. Now let's look at the diagram. Now from the diagram, if you look at this diagram, the shaded part here is a major segment. Then this other part will be the major segment from that definition. Now let's look at sector. A sector. Now a sector, it is the area bounded by the radius, by the radii, that is plural of radius, showing major and minor sectors. Now let's look at the diagram again. Now from the diagram, why do we use the word radii? You see OC is a radius, OE is a radius. So this is a sector. So you have, this is radius, so radii. Now, so this is a minor sector. So the other part will be the major sector. So that is what a sector is. Now, we have cycle theorems. We have so many of them, but let's look at the properties of cycle theorem, because the most important thing now is the application, not just the theory. It's the application that matters a lot. Now from the properties, let's start with the first one that I have here. angle at the center is twice angle at the circumference. Now if you look at the first diagram here, from this diagram, you find out that this angle here is at the center. This one is at the circumference. So if this angle is x, this one will be 2x. What we are trying to say is that if this angle here is 80 degrees, this one is at the circumference. For you to get this angle, you have 2 times 80, that will give you 160 degrees. That is why you say angle at the center is twice angle at circumference. Now look at this diagram again. If you look at it, this one it is at the circumference, but this one is at the center. Take note, it's more of a tribal mark. Now if you look at this one, why is it angle at the circumference? The angle is touching the circumference. That is why we say angle at the circumference. But this one here, O here, it means center of the cycle. So angle at the center. So the same thing, if this angle is 30 degrees, this one will be 2 times 30, which is 60 degrees. And that is why we have this explanation here. That angle POQ equals twice angle PRQ. That is for the first diagram. Now for the second diagram, angle POQ equals twice angle PRQ. Now let's go to the third diagram. The third diagram. Now, from the third diagram, we have PQRO. Now you find out that PRQ, this angle here, is at the circumference. It's at the circumference. But POQ is at the center. So that is why this angle is twice this. Now, if this angle here is 120 degrees, that is at the circumference here. Now, the angle here at the center will be 2 times 240. That will give 2 times 120. That will give you 240 degrees. That is why we have it here. Angle POQ is twice angle PRQ. That is the first property. Now the second property we have, which is also linked to the theorems, we have the angle in a semicircle is 90 degrees. That is right angle. Now we have here, you look at the first diagram, we have A, B, C, D. Now we have this. This is a straight line bisecting AC. Now you have this. This is the center here O. Now the angle here is 90 degrees. It's at the circumference. Then the angle here is 90 degrees. So angle in a semicircle. That is why here we have it. ABC is 90 degrees and angle A. So now let's look at the second diagram. The second diagram. Now if you look at the second diagram, this is a semicircle. Now from the semicircle, what we are just saying is that this angle here is 90 degrees. We are not proving anything, we are explaining. Now this angle, so whenever you have a semicircle, you will see you must have a center mark O, then the angle at the circumference. So now for this one is not included in the work here. But what we are saying is that this angle here is 90, this angle is 90, angle in a semicircle. The same thing here, this angle is angle in a semicircle. Now if you look at it, this one, AOC, is angle on a straight line. You know that angle on a straight line is 180 degrees. Sum of angle on a straight line, AOC. So this one, and if you look at it, AOC is at the center. And we say that angle at the center is twice angle at circumference. So your ABC is at the circumference. So to get this angle is 180 divided by 2. That is 90 degrees. Because this one is at the center, this one is at the circumference. Now we have C. Angles in the same segment are equal. Now if you look at the diagram here, this angle E angle D, angle C, they are the same. What we are trying to say is, if this angle here is 60 degrees, this one is 60 degrees, this one is 60 degrees. Angles in the same segment are equal. Now you must take note. You see, you have, this is the center here, O. So that is why here we have angle AEB. AEB, this angle here, is the same thing as angle ADB, which is this, the same thing as angle ACB. Now, let's look at the next property there. The next property, angles in opposite segment are supplementary. Now, in some textbook, you find out that it may be opposite angle of a cyclic quadrilateral are supplementary. It's the same theorem. So, and it's the same thing as angles in opposite segment are supplementary. That is, they add up to 180. Now, there is an important condition here that you must take note of. You see, ABC is a cyclic quadrilateral. This condition, it must have to be a cyclic quadrilateral. So, ABCD is a cyclic quadrilateral with center O. This condition must be satisfied before you apply this theorem. Now, what we are simply saying is that this angle and this plus this will give you 180. Now, in X, assuming X is 120 degrees, you can find Y. We have X plus Y is 180, but our X here is 120. So 120 plus Y is 180. So our Y will now be 180 minus 120. 180 minus 120 is 60 degrees. Y will be 60 degrees. The same thing, N plus N is 180 because we say they add up to 180. So if N is 80, you can now get N. If you like, 180 minus 80, that will give you 100. Now let's move on to the next theorem. The next theorem, that the exterior angle of a cyclic quadrilateral is equal to the interior opposite angle. Now, this condition must also be satisfied. You must have a cyclic quadrilateral first. Like in this case, we have A, B, C, D is a cyclic quadrilateral, and possibly with center O. Now, if you look at this angle here, it's at the circumference. Now, this X equals to Y. That is what we are saying. Angle X will be equals to angle Y. Now, let's look at something here. Assuming this angle here is 80 degrees. Now, let's go up. Up. We say that this angle X plus Y is 180 from this theorem. That is, this angle plus this will be 180. So that means to get this angle here, you have 180 minus 80. That will give you 100. So this angle here is 100. Because this and this, they add up to 180 because they are supplementary. They are supplementary. Now, if this angle here is 100, if this angle is 100, how can we find this angle here? Angle on a straight line to find Y. So we now have 180 minus 100. That will give us 80 degrees. Angle on a straight line. So that is why we say that the exterior angle, that is this angle of a cyclic quadrilateral, is equal to the interior opposite angle. Now F, we have a tangent, a cycle meets in one point only. What we are trying to say is, you have a cycle, you just have a tangent. A tangent, just one tangent. Now, whenever you have a cycle and a tangent, now you discover that this is the center of the cycle. Now, the angle formed here must be a right angle triangle, which is 90 degrees. Now, I say take note, most of these theorems, they are more of a tribal mark. Now, we have here angle ATO. ATO, this angle, is equal to angle BTO. That means here is 90 degrees, here is 90 degrees. Because we know that sum of angles on a straight line is 180 degrees. Now here, what reason do we have? AB is tangent to OT. AB is tangent to OT. Or we can say radius perpendicular tangent. Now let's look at the next property there. Now G, which is the next property, the tangents, plural, the tangents to a cycle. You have two tangents, but you have one cycle. The tangent to a cycle from an external point are equal in length. Now, this is the first tangent. The first tangent, and this is the second tangent. They meet at, let's call this place T, the tail T. Now, here you find out that you have this one is a straight line bisecting this. Now, since it is bisecting this, it implies that this angle has to be equal to this. And that is why, so if x is 30 degrees, y is going to be 30 degrees. Now, here we have, this is the center O, and here is a straight line to this. Now, this is an isosceles triangle here. It's forming an isosceles triangle. So that you know that in isosceles triangle, the base angle are equal. This angle is equal to this. Now, if you look at this, AT equals to BT. This is our AB. AT equals to, this is AT equals to BT. In length, if this length is 20 centimeters, this length will be 20 centimeters. Now, in the same way, we have angle ATO. This angle here, ATO, which I have explained, is equal to angle BTO, that is BTO, which I have explained here already. Now, you have angle AOT, angle AOT, this angle here, that is M, is equal to angle BOT. That is M equals to M. So if this angle here is 40, this one will also be 40 degrees. Now, here we have OBT. OBT is the same thing as OAT, which is 90 degrees, radius perpendicular tangent. Let's go back to the other theory, this one here. Now, what I'm explaining is from this one, a tangent to a cycle. Now, so we have here, you have to take note of this. OT bisect AB at right angle. That is why we have right angle here. Now, we are going to look at the last property. I said the last property here, we have angles in the alternate segment are equal. Angles in the alternate is different from angle in the same segment. Angles in the alternate segment is different from angles in the same segment. Here we are dealing with angles in the alternate segments are equal. Now, this condition needs to be satisfied. One, we have a cycle, we have a center, and we have a tangent. Now, what we are saying is that, you see, this angle here is equal to this angle. This angle is equal to this. That is why we have it here. ATB. ATB is a tangent. That is why I say it's one of the conditions that have to be satisfied. So it's a tangent to the cycle centered O. O is the center of the cycle. Now, angle BTC. Angle BTC. That is this angle. This angle equals to angle TDC. TDC. This angle is equal to this. The same thing, angle ATD. Angle ATD. This angle equals to angle TCD. TCD. So that is just what you need to know. Now next, we'll move into application. Now, like I said, let us look at application. So we are going to look at application of cycle theorems. What we have to look at. Now we have an example here. Find the angles x, y, and z in the diagram below. This is a diagram. O here is the center of the cycle. Now we cannot just solve this. There is a particular theorem or properties of cycle geometry that we are going to apply to solve this. Now let's look at the theorem once more. Let's look at the theorem here. Now, if we can recall this theorem that angle at the center is twice angle at circumference. Now, angle at the center is twice angle at circumference. This angle is at the center. This one is at the circumference. So if this one is 80 degrees, this one will be 2 times 80, which is 160 degrees. Now let's go back to our question. Now, since we have to find x, y, and z, now if we look at this angle here, it's at the circumference, but angle z is at the center. So it means that angle z is going to be 2 times 126, which is going to give us 252 degrees. It's going to give us 252 degrees. 252 degrees. Reason: angle at center is twice angle at circumference. So now this angle is 252 degrees. Now, how can we find angle x? Now, angle z is this, which is 252 degrees. Now we can find x. We can now find angle x, which is angle at the point. And we know that angle at the point is 360. Now let's look at something here. Let's look at something. Now if you look at these angles here, they are angle at the point. By the time you add this, 120 plus 60 plus 120 plus 60 here, you have 360 degrees. Now let's go back to our question. Now, to find this angle, angle x is going to be 360 minus 252. This will give us 8. And this will give us 0. This will give us 1. So our x is 108 degrees. 108 degrees. And the reason is angle at a point. Angle at a point. That is just the reason. Now, if this angle here is 108 degrees, now this one is related to this. This one is at the center. This one is at the circumference. So to find angle y is going to be 108 divided by 2. And that will give you 54 degrees. Because angle at the center is twice angle at circumference. So since it is angle y that we are asked to calculate, we will now say angle at circumference is half angle at center. So that is the solution. So our x is 108 degrees, our y is 54 degrees, z is 252 degrees. Let's look at second example. Now, in the second example, in the diagram, TA is a tangent to the cycle at A if angle BCA is 40 degrees and angle DAT is 52 degrees. Find angle BAD. Now, this is a diagram here. Now, from this diagram, if you look at the theorem that we have, the properties of those theorems that we have considered, this one is tangent. We have tangent to a cycle. Remember I told you the condition that it was met? Here, if you look at it, this angle here will be equal to this. And the angle here will be equal to this. That is opposite angle, alternate angles of a alternate angles. This angle is equal to this. this angle is equal to this. Now let's look at how we are going to solve this. Now, in solving this, you find out that angle DAT equals to angle ACD equals to 52 degrees, alternate segment. Now, let's come back to the diagram. Let's come back to the diagram. We say that angle DAT, this is DAT, this angle is equal to angle ACD. That means if this angle is 52, this angle here is 52 degrees, alternate segment. So take note, look at the board. That is why we have 52 degrees here, alternate segment. Now, let's come back to the diagram. Now, if you look at the diagram, angle BCD is going to be angle BCA plus DCA, which is what? 40 plus 52. 40 plus 52, and that will give you 92 degrees. What we are saying is that if you add this plus this will give you 92 degrees. That is why we have this. We have this here, 92 degrees here, 92 degrees. Now, let's come back to the diagram. Let's look at the diagram again. Now, from the diagram, we are asked to find angle BAD. Now, we are interested in angle BAD, this angle here. Now, if you look at this angle and this, they are opposite angle of a cyclic quadrilateral. And we say that sum of opposite angle of a cyclic quadrilateral add up to 180. So, we are going to have BAD plus 92 equals 180. Let's look at it here. That is why we have BAD is 180 minus BCD, opposite angle of a cyclic quadrilateral. So that is why we have 180 minus 92. We have 88 degrees. That is the solution. Now, example 3. In the diagram, PQRS is a cyclic quadrilateral. Now, if angle QPS is 105 degrees, and angle PRQ is 31 degrees, you have to find 1, X, 2, Y. Now, if you look at this, if you check the properties under alternate segment, angles in the same segment. If you check the theorem under angles in the same segment, you discover that this angle and this, they are on the same segment. So, this angle, that is why here we have angle PSQ, which is X, is equal to angle PRQ. So, this angle is equal to this. Angles in the same segment. That is why our X is 31 degrees. X is 31 degrees. But we know that to find Y here, what we are going to do, if you look at P and Q, angle P plus angle R here, this is angle P, angle R. If you add this and this is 180. That is why we have 105 plus this angle here, which is 31 plus Y equals 180. Y, opposite angles of the cyclic quadrilateral. They add up to 180. So you now open this bracket, 105 plus 31 plus Y equals 180. Now you now collect like terms. So you have 180 minus 105 minus 31. That will give you 44 degrees. So Y is 44, X is 31 degrees. That is the solution to this problem. Now let's look at the fourth question, the fourth example. In the fourth example, we have in the diagram, O is the center of the cycle, and ABC is tangent at B. ABC is tangent at this point B. If BDF, angle BDF, which is this angle, is 66 degrees, and angle DBC, which is this angle, is 57 degrees, you have to calculate angle EBF. Now, if you look at this diagram very well, you discover that there is a semicircle somewhere. Now, if you look at this is angle in a semicircle. So that means this angle here is 90 degrees. Angle in a semicircle. Remember the properties. Angle in a semicircle is 90 degrees. That is why we have this. BD is 90 degrees. Angle in a semicircle. Now, how can we calculate this angle here? The angle here. This angle. Now, since the whole of this is 90 and this is 66, so we are supposed to have 90 minus 66, and that will give us 24 degrees. So this angle is 24 degrees, because 24 plus 66 will give us 90. That is why here we have angle EDF is 90 minus BDF. That is why we have 90 minus 64, which is 24 degrees. Now, if this angle here is 24 degrees, but the angle we are asked to calculate is EBF. Now, if you look at the diagram, EBF, which is this angle here, if you look at this angle and this angle here, this one, this angle and this, they are angles in the same segment. So this angle will be 24 degrees. Angles in the same segment. That is why we have EBF equals to EGF equals to 24 degrees. Angles in the same segment. True. Let's look at the question again. We are asked to find BGF. Angle BGF. This angle here. BGF. Now, we know that this angle here and this, if this is 57, this will be 57. Alternate segment. This and this are alternate segments. So if this is 57, this is 57. That is why we have it here. Look at it here. BED equals to CBD, which is 57 degrees. Alternate segment. So if this angle is 57, this angle is 57. Now we are interested in this angle. We are interested in angle BGF. And we know that sum of angles in a triangle is 180. So to find this angle, we will now have 180 minus this plus this. And when you add 57 plus 24, you are going to have 81. So that is why we have 180 minus 81. That is giving us 99 degrees. This angle, 99 degrees. That is all. Now, the fifth example in the diagram below. A, B, C, D is a cyclic quadrilateral. A, B, C, D. This is a cyclic quadrilateral. And lines AB and DC and line DC produced at E. That means they meet at E. If angle BCE, this angle is 95 degrees, and angle ADC, this angle is 62 degrees. Calculate one, angle BAD, angle BAD, that means small a. Now, if you look at this, you find out that you can solve this in two ways. But you see, if this one, this is 95 degrees, you can find this angle here, BCD, which is 180 minus 95. That will give you 85 degrees. Angle on a straight line. So this one will be 85 degrees. Angle on a straight line. That is why you have it there. Look at the solution here. We have angle DCB is 180 minus 95, which is 85 angles in a straight line. Now let's go back to the diagram. Let's go back to the diagram. Now, in the diagram, if this angle here is 95 degrees, now we know that ABCD is a cyclic quadrilateral, but opposite angle of the cyclic quadrilateral are supplementary. That means the opposite angle add up to 180. So it means that angle A plus, that is small a now, plus 85 is equals to 180. That is what we have here. Let's go look at it here. A plus 85 is 180. Then you now make a subject of the formula. So you now have A will be 180 minus 85. That is 95 degrees. Opposite angles of the cyclic quadrilateral. Let's go back to the question. Let's go back to the question. So this angle, we have 95 degrees. Let's go back to the question. The second question, we are expected to calculate angle BEC. Angle BEC. This angle here, angle BEC. Now, we found out that we know that if you look at this is 95, 62, 85. And if you look at ABCD, it's a quadrilateral. And sum of angles in a quadrilateral is 360. So you can find this angle. Or another way you can solve it. This angle here is 62 degrees. That is another theorem. Opposite angle of exterior angle. Exterior angle of a cyclic quadrilateral from that theorem. So if this is 62, this is 62. Exterior angle of a cyclic quadrilateral. Look at it there. Now, if this angle is 62, this one is 95, and we have to find this. And we know that sum of angles in a triangle is 180. So we are now going to have 180 minus 62 plus 95. That is what we have here. Therefore, angle BEC is 180 minus, this is 62 plus 8. But our A is 95. That's why we have 62 plus 95. So in place of A, we have 95. If you add, you are going to have 157. So 180 minus 157, that will give you 23 degrees. So that is the solution to this question. Now, we'll look at the next example.